Let's talk about the largest, most ambitious construction project in history. I mean, this thing took 4.5 billion years to complete, used materials forged in dying stars, and it laid the literal groundwork for every single city, every building, and every road on the planet. So today, we're going to open up the blueprints for that project, the formation of Earth itself. Okay, so as a planner, you deal with layers all day, right? You've got your zoning layers, your infrastructure, your social layers. But let me ask you this. What do you think is the single most important physical layer of your city?
Well, it's not the pavement, it's not the pipes, or even the topsoil. It's the bedrock. It's that ancient geological foundation that pretty much dictates everything that can happen up on the surface. So, to really understand our cities, we've got to go back and understand how that foundation was built in the first place.
Our story doesn't even start on Earth. It starts way out in the vastness of space. Think of this as phase 1 of the construction project, just gathering up all the raw materials.
Now, the big idea, the main blueprint for this whole process, is something called the solar nebula theory. It's basically the leading explanation for how everything, our sun, the planets, all of it, came together from this massive spinning cloud of cosmic gas and dust.
And here's a really simple way to picture it. Imagine a tiny speck of dust in that cloud. As it spins around, it bumps into other specks, and they kind of stick together. It's basically like a giant snowball rolling through space, just getting bigger and bigger and bigger. That whole clumping process, it's called accretion. And this breaks it down perfectly. So first you get the collapse of that giant cloud. Then the center gets super dense and hot, and boom, it ignites and becomes our sun. All the leftover stuff flattens out into a spinning disk. And inside that disk, that snowball effect, accretion takes over, building bigger and bigger chunks until, eventually, you get planets. Okay, so moving on to the next critical phase. We've basically assembled a planet, but right now it's just a huge, uniform ball of hot rock. Now comes the sorting process, organizing all that raw material into a structure that actually works. The key to all this sorting was heat. I mean, a ton of heat. Early Earth was just constantly being slammed by asteroids and comets. All that energy, plus pressure and radioactivity, turned the entire planet into a molten magma ocean. Everything was liquid. And when everything is liquid, a super simple principle takes over. It's one you see every single time you make a vinaigrette for a salad. All the heaviest, densest stuff sinks straight to the bottom, and the lighter stuff just floats right to the top.
This planetary salad dressing effect, well, it has a formal name, of course. It's called geochemical differentiation, and it's the fundamental process that transformed Earth from just a big, homogeneous blob into the layered planet we live on today.
So what sank and what floated? Well, the really heavy elements, mostly iron and nickel, just plunged down towards the center to form the planet's super dense core. And the lighter materials, which we call silicates, basically the stuff that makes up most rocks, they floated upward and eventually formed the mantle and the crust. And that outermost lightest layer, the crust, that's the one that really matters to us. It's the layer we live on. You can think of it as the final pour in this planetary construction project. It's the direct foundation for every single city. But here's a key thing. Not all crust is created equal. You've got the dense, thin oceanic crust. Think of it like a heavy floor tile that makes up the bottom of our oceans. But then you have the thick, much less dense continental crust. For this one, picture a big, buoyant slab of styrofoam. And it's this lighter, styrofoam-like crust that floats higher and forms the continents where we actually build our cities. So how did we get this continental crust? Well, as the mantle below it churned and partially melted, the lightest, kind of frothiest parts of that melt rose up to the top. Then it cooled, hardened, and created these stable platforms that we now call continents. Okay, so we've journeyed all the way from a cosmic gas cloud to solid ground. Now we get to the most important part. How do we connect this epic geological story directly to the actual blueprint of your city?
So just as a quick recap of the project timeline, we start with the collapse of the nebula, then the sun and disk form. Earth comes together through accretion, then you have that great sorting event of differentiation, and finally, the cooling that gave us a stable crust. This whole multi-billion-year process set the stage for, well, everything.
So here it is, the big question. Why should a city planner who's working on, say, a 25-year comprehensive plan even care about a process that took billions and billions of years to unfold? Well, because the end result of that whole process, the specific type of bedrock sitting right underneath your city, it dictates almost everything. Seriously. It determines how stable your building foundations can be. It controls your seismic risk, which informs your building codes. It dictates where you find groundwater, where you can source sand and gravel. It's literally the invisible blueprint for your entire built environment. And this quote from our source material really just sums it all up. That one sorting process, differentiation, didn't just give us the crust. It set the stage for plate tectonics, for the magnetic field that protects our planet, and for the entire evolution of Earth's surface. It really is the master process behind it all.
And that brings us right back to where we started. Every city is built on a foundation that has a story stretching back billions of years. And understanding that story isn't just for geologists. It's the very first step in sound urban planning. So take a look around your own city. What story is written in its bedrock?